session is entitled iframe rate for 3D time-of-flight cameras by dynamic sensor calibration. The authors are Mirko, Schmidt, Klaus, Zimmermann, and Bernd. Jähne. They are from University of Heidelberg and sunny Germany. And I have to mention that Mirko is looking for a job. So Mirko.
Thank you. Hello. I will speak about time-of-flight cameras today. These are cameras which are able to acquire depth images of dynamic scenes. So, as visualized here, just an image comprising a depth information in each pixel. And these depth maps are very useful in many different applications. For instance, in the field of machine vision, gaming, medical applications, automotive, and so on. The basic principle of all time-of-flight cameras is to measure the time which the light needs to travel from a modulated light source to a target and back to the camera. And from that time, which is determined in each pixel, the depth is computed. This involves the acquisition of multiple measurements, and these cameras also acquire multiple raw images which are combined in order to generate one depth map. And for this reason, time-of-flight depth imaging belongs to the class of computational photography. This slide gives a very short outline of this talk. I will go into details for each of these points. As I mentioned, there are a multitude of n samples required to generate the depth map, and sensors have been realized which perform multiple of these measurements in parallel. This is done by employing multiple detection units. I also call them tabs here, in single pixels. And a typical implementation is that 4 measurements are required and sensors are used which employ 2 detection units per pixel. The problem now is that these different detection units suffer from different systematic errors, and these differences would introduce distortions in the reconstructed depth map. So the state-of-the-art technique to prevent these distortions is to measure each necessary sample by use of each of the tabs separately and then to perform an averaging. So this is slow because more or less the same information has to be acquired multiple times. Our approach seeks to dynamically calibrate these different systematic errors and to perform a correction of the raw data. So this enables to compute multiple depth maps from the same amount of raw data and thus results in an increase of the frame rate. One word about related work. There were some publications about the calibration of time-of-flight imaging systems aiming at a reduction of the systematic errors of the processed channels. So for instance, Kalman, Lindner, or Raab presented papers. There was work about the raw data acquisition process of such cameras and how the errors occurring during that process result in distortions of the generated depth map. And this was mainly published by members of our group, so for instance by Mr. Ertz and by myself. And concerning this approach presented here of enhancing the frame rate of a time-of-flight system by use of software, there is basically, or to our knowledge, there is no real related work, but more details about this technique will appear in my thesis, which will be in July. The principle of continuous wave time-of-flight cameras is to use a light source, which is temporarily modulated, so the intensity varies over time, and this light source illuminates a target. The backscatter light is still modulated, and now a special sensor is used which measures the correlation function of the incident optical signal with an electronic reference signal. And from this correlation function, or from these samples, the phase shift between both signals can be determined, and this phase shift then gives the distance Z. The correlation function can be derived theoretically, for instance here, assuming a sinusoidal modulation of the light source and a rectangular reference function. Then the correlation function is given as this here. Here are three unknowns, which are the offset and amplitude and the phase shift, which gives the depth then. And from 4 samples of this function acquired at the angles theta of 0, 90, 180, and 270 degree, using these reconstruction formulas given here, these unknowns can be determined. Now I would like to explain how such a sensor, which is able to measure the correlation function, is implemented. And for that, I would like to recall how a conventional 2D imaging sensor works. This is visualized here. A number of photons hits the surface of the sensor and generates electrons, which are stored in a quantum well, converted into voltage, amplified, digitized, and at the end given out as a digital number which represents the intensity of the incident light. The 2-tab imaging device uses or has doubles this complete chain here, and it uses an electronic switch, and their function is now that the incident photons again are generating electrons, and these are sorted into the one or the other quantum well by use of the switch. And the idea is now to synchronize this switch with the light source, and by doing that, these numbers giving out at the end correspond to samples of the correlation function of both signals. So this sensor is able to acquire 2 samples of the correlation function in parallel. The sample of the angle theta and a sample which is shifted by 180 degrees to this angle. So here are the 2 tabs, which I call A and B here, and the problem now is that these 2 amplification paths here have different characteristic curves, so the photo response to the 2 tabs is different. This different photo response would result in errors, and as I mentioned, there is averaging techniques to prevent these errors. A typical raw data package acquired by a camera looks like shown here, so this axis here is basically the time. So, and while tab A acquires a sample at 0, 90, 180, and 270 degree, tab B acquires a sample at 180, 270, 0, and 90 degree. And then samples describing the same angle theta, so for instance A 0 degree and B 0 degree, are averaged, and these averaged samples are then used to compute their phase shift and from that the distance. So our idea is simply to split this raw data package because the 2 halves of the package now contain in principle the same information. So you have all required samples, meaning all angles measured by each half. But the problem is, and the idea is then that this enables to compute 2 independent depth maps of using the same data. But the problem is that this splitting is not possible because of the because of the mentioned different photo response of the taps. So there's some correction required. And we are doing this correction by employing a dynamic calibration technique. So we look at the signals, the temporal signals of single pixels. And here in this figure, the theoretical signal of the two corresponding measurements A and B at the angle 0 degree are given. So you can see that these signals are not identical because of the different systematic errors, but they are correlated somehow. And we measure this correlation. These are the samples now. We measure this correlation by detecting static subsequences of the signal, and from that we extract pairs of corresponding measurements, and these pairs are then used to compute the correlation. In this plot you can see the all possible pairs of measurements performed with tab B at a given measurement angle and tab 1. These are all possible measurements of an arbitrary sequence, and now we detect these pairs of the static subsequences and perform the calibration by fitting a linear polynomial to these pairs. So this is an implicit calibration which enables to rectify the data acquired with one of the taps. So this rectification then can be done just by evaluating the polynomial with data acquired by the tab B. And what we get is rectified data. So we have a measurement acquired with tab B, put it into the polynomial, get out some data, and this data corresponds to the data which would have been acquired with tab A if the same input would have been present. So this then enables to split the raw data packages because the averaging technique is no longer required. And this calibration process has to be done for all measurement angles theta and all pixels individually. I will show now a short video which visualizes the process of gathering this calibration data. On the left side you see the depth map of the scene, which was acquired in the lab just by tilting the camera a little bit. And on the right side you see the figure I've shown on the previous slide with the correlation and the collecting of the corresponding pairs for this single pixel which is marked here. So you can see when the camera is moving that different points here are found to be in static subsequences, and and what we get at the end is the mentioned operator which enables to rectify the data. What you can see on the left is the final image of the sequence. It shows a rotating target, and you can see these artifacts here, these motion artifacts occurring at the edges perpendicular to the motion. And these result from the fact that the raw images are not acquired instantaneously, but they reflect different states of the scene. So while the scene is moving at these edges, reconstruction is incorrect. I will come to this back later. This shows the result of the algorithm. Here is a raw data package of 1 pixel and the result of the conventional averaging technique. When we split the raw data package and do not use any correction of the raw data, we get these strong artifacts here. And if we use our proposed calibration technique, we get 2 single depth maps. And when you look at it, you can see the motion of the target. It's probably hard to see. We evaluated these results quantitatively by analyzing the consistency of the generated single depth maps. This was done by comparing these 2 single depth maps without any correction and these which were created using our technique. The error was defined basically as the standard deviation of the difference of the depth measurements of all pixels within a patch, which is shown here. And for the single depth maps generated from uncorrected data, we get a consistency error which is about 2.8 meters, whereas our technique gives an error which is 0.1 meter, so it's about 28 times better. We also analyzed the temporal noise by analyzing a stack of 25 consecutive depth maps. This one generated using the conventional averaging technique compared to 1 depth map generated using our technique. The results, and this error was just a standard deviation of the depth measurement of single pixels, and this was averaged over the whole patch. For the averaging technique, we get an error of 0.048 meters, and our method gives an error of 0.0699 meters. So this fits very well to our expectation of an increase of the error of the standard technique by a factor of square root of 2. And this factor results from the fact that about a half of the light is used to generate a depth map. Yeah. Another important result is that the artifacts, which I mentioned before, are significantly reduced. For these artifacts, the number of forces between their required acquisitions is important. So the conventional averaging techniques uses 4 acquisitions with 3 forces between them. So this gives 3 regions which are disturbed by artifacts at the edges. And one of the single depth maps is generated using 2 acquisitions, which has only 1 pulse. So we get only one, or we get an error which is disturbed by the artifacts, which has only a third of the size of the conventional technique. So the motion artifacts are reduced by a factor of 3. So now I come to the conclusion. We presented a dynamic estimation technique of the inequalities of the different taps and multi-tap time-of-flight sensors. The derived raw data correction enables to compute multiple depth maps from the data which was previously used to compute only 1 depth map. So it is possible to increase the frame rate significantly. In our experimental verification, we were able to double the frame rate. So the system now gives a performance of 60 to 80 hertz at a spatial resolution of 200 by 200 pixels. And these are independent depth measurements done in each pixel. To our knowledge, that is the fastest depth measurement done with time-of-flight cameras so far. We have shown that these single depth maps are consistent and that the temporal noise increases as expected. And this technique furthermore effects and a significant reduction of the motion artifacts. To give an outlook, our technique now uses static subsequences. If these are not given in certain applications, it would be possible to use a temporal interpolation of the raw data signals. These estimated calibration parameters, they are not stable over time because they depend, for instance, on the temperature of the system. So it would be beneficial to introduce some temporal adaptation of the estimation process. A further point is that the temporal sampling of the required raw images should be adjusted. At the moment, these are acquired in a burst mode fashion as it is shown here. So you see the time arrow, and the system performs 4 acquisitions, and then there's a long delay. So it would be good to adjust these raw images such that they're corresponding, or that the result of the depth map computation corresponds to an equitemporal sampling of the scene. And I would like to mention that future sensors will profit even more from this technique. Future sensors using more taps than only 2, because the speed up of our method compared to the standard method is equal to the number of taps used by the sensor. Okay, then I would like to finish here and thank Sony Deutschland for funding this work, and I would like to thank you for your attention. Thanks.
We have time for a few questions.
Why might algorithms be used for optical coherence tomography, where we can get micron resolution depth?
Yeah.
I wonder if you can scale up that technique for this purpose. It's based on
OCT.
shading.
I don't think so, because you mean you could use OCT for medium range?
Yeah, scale that up.
Yeah, but then you would need light with, maybe with terahertz technique also.
What? I mean, you can use light, right? You don't need to get a single map. But instead of using a super barband for like the micron coherence lens,
Yeah.
you can use whatever coherence lens you want, just to match your resolution or even do better.
Yes.
You don't have to, 6 centimeter resolution. You can design the bandwidth to have a 6 centimeter coherence lens.
Yeah, but here we have a much, the measurement range is much higher, but the resolution is worse compared.
It's better, people have achieved like down to a micron resolution.
Yeah, but in OCT you are not able to acquire an image like this one. In OCT you have small scale objects.
So you can scale everything up.
Yeah, but then you have to scale the light to another wavelength.
No?
No?
I don't understand. You scale the coherence lens. You don't have to scale the light wavelength. We can discuss later.
Okay.
Maybe you can take it back.
Okay.
Maybe the next paper.
I wonder if there is any theoretical limitation of the minimum or maximum depth that can be measured by the focus.
Yeah, there are limits given by at the moment they are given by the sensor manufacturing process. These sensors are able to switch very fast, so the dark currents are quite high, and so you get a lot of fixed pattern noise and things like that, and statistical noise. But theoretically, you can, by changing the modulation frequency of the light source, you can adapt the range in which you would like to measure. So there are applications, for instance, in automotive. Audi is using these cameras, and they have to measure about 200 meters or so. And on the other side, there are endoscopic applications where you want to use these cameras in a very small volume, and you have maybe 10 to 20 centimeters or so measurement range, and then a much higher resolution.
So next our speaker again, and all the speakers who made the presentation.
Couple of announcements before you leave. I know you're all hungry, so food is waiting for you. So you all have these white tickets, so you can just give one of them for a lunch box. There's, I think, 5 different varieties or something. So it's the standard lunch box, sandwich, and so on. So it's very hard to find food nearby on a weekend here.